Hello, I'm Ella Sharkansky, and I'll present the Chernoff bound for high-dimensional expanders. This is a joint work with Professor Tali Kaufman. First, let's go over our motivation behind this work. As you probably know, expander graphs have countless applications in computer science, mathematics, and even physics. One essential and useful property of expander graphs is the expander Chernoff bound. Recently, there is growing interest in high-dimensional expanders. A notable example is a paper by Anari, Liu, Garan, and Vincent, where they use random walks on high-dimensional expanders to solve a major open problem on counting the bases of matroids. Our goal is to generalize the expander Chernoff bound to higher dimensions. The naive generalization doesn't work because in high-dimensional expanders, there are abstractions that don't exist in one-dimensional expanders, and we'll see how to overcome them. Now, a quick overview of our results. We prove a one-dimensional expander Chernoff bound for shrinking functions. We then prove our main theorem, which is the high-dimensional expander Chernoff bound for functions from high levels. And our last theorem is more of a bonus theorem about a very useful method for studying high-dimensional expanders. We prove that the almost orthogonal decomposition of the space of k-Cochains by Dickstein, Dinur, Filmus, and Harsha is actually orthogonal in good enough high-dimensional expanders. Now, let's go over a few definitions. The first definition is expander graphs. Let's say we have a graph that is weighted, undirected, and connected. We can have a walk on this graph where the probability to go between two vertices is determined by the weight of the edge between them. This walk has real eigenvalues between -1 and 1, where the largest eigenvalue is 1. We denote lambda g to be the largest eigenvalue in absolute value, except for lambda 1. G is a two-sided lambda spectral expander if lambda of G is smaller or equal to lambda. This is the definition of expander graphs that we're using. A good expander graph, we say that an expander graph is good when lambda G is very close to 0. Another definition is the stationary distribution of a random walk, which is the probability distribution on the vertices that the walk is trying to reach after an infinite amount of steps. Now, let's say we have a function f on the, and we want to estimate its expected value, but we don't take random samples of f, and instead we walk on an expanded graph, and we take the average of f on this walk. The expander Chernoff bound says that the probability of the distance between the sampled average of f and the actual average of f to be greater than epsilon decreases exponentially as t increases, where t is the amount of steps or samples. This is denoted in equality 1. In addition, because our samples are not independent, we have s in the exponent, where s equals 1 minus lambda 2 of g. So if G is a good expander, S is very close to 1. Now, to define high-dimensional expanders, we first need to define pure abstract simplicial complexes, because expander graphs are built on graphs, but high-dimensional expanders are built on a structure called pure abstract simplicial complex. So in an undirected graph, we have vertices and edges, where each edge is a set of two vertices. We can generalize this concept to sets of more than two vertices. For example, a set of 3 vertices is called a triangle. All of those sets are called faces, and the dimension of a face is its size minus 1. For example, the dimension of a vertex is 0. Now, a pure abstract simplicial complex is constructed by first taking d-dimensional faces and then adding all of their subsets. our complexes are also equipped with a probability distribution, pi d, on the d faces, the d-dimensional faces, and induced distributions, pi k, on k faces. Now, to define high-dimensional expanders, we first need to define the link of a face. Given a face tau, its link is another complex where we take all of the faces that contain tau, and then we remove the vertices of tau from each one of them. This is basically the local view of tau, and it's another complex called the link of tau. Another definition is the underlying graph of a complex, which is basically just its vertices and edges. Given a pure absolute simplicial complex, it is a gamma local spectral expander if for every face, the underlying graph of its link is a gamma spectral expander. This is the definition of high-dimensional expanders that we are using. Okay, so now when we think about Chernoff band for one-dimensional expanders, this is actually not a bound for graphs. It's a bound for walks on graphs. So to discuss the high-dimensional expander Chernoff bound, we first need to decide which walk we're studying. And the walk we are studying is called the lazy upper random walk. We study this walk because it's very related to the structure of the complex. So this walk walks on k faces, and given a k-dimensional face tau, it first chooses a k+1 face that contains tau according to the distribution pi k+1, and it then removes one vertex of this k+1 face at random. So this walk is denoted mk+, and it walks on k faces. Another definition is ckx, which is the space of k-Cochains, where a k-Cochain is a function from k faces to the real numbers. And as a walk operator, mk+ is from ckx to ckx. In addition, ckx is equipped with an inner product, which is like the standard inner product normalized by pi k. Now, we can just apply the expander Chernoff bound that we saw earlier to the higher order random walk mk+ to provide a high-dimensional expander Chernoff bound. So we get the same bound as before, as in inequality 1, and now S equals 1 minus lambda 2 of mk+. Unfortunately, lambda 2 of mk+ is about k+1 over k+2, which approaches 1 as k increases. It means that even if the complex is a very good high-dimensional expander, still the bound is bad because S is getting closer and closer to 0 as k increases. So this is why we call it the naive high-dimensional expander Chernoff bound, because it doesn't capture the expansion of the complex. The reason behind this is that in high-dimensional expanders, there are abstractions that don't exist in one-dimensional expanders. And these abstractions make some of the eigenvalues of mk+ large. Our idea is to avoid these abstractions, because if f is a good function, meaning not an abstraction, it shouldn't pay for the complex having abstractions. To define this in a more formal way, we define the shrinkage of a vector. So given a finite dimensional inner product space W and the self-adjoint operator M from W to W, W can be decomposed to the eigenspaces of M. And given a vector U in W, it can also be decomposed to the eigenspaces of M. We define the shrinkage of W, denoted lambda of W. We define the shrinkage of U, denoted lambda of U, to be the maximal eigenvalue in absolute value that its eigenspace is part of the decomposition of U. For example, if W equals to a direct sum between the eigenspaces of 1, 1/4, 1/3, and half, and U is in the direct sum of the eigenspaces of 1/4 and 1/2, and 1/4 and 1/3, then lambda of M equals half, whereas lambda of U is just third. Okay, so the first theorem we prove is the expanded Chernoff bound for shrinking functions. Given a random walk on a lambda expander G with a stationary and initial distribution pi, and a function f on the vertices with expected value 0, which is between -1 and 1, we denote pi star to be the minimum of pi. Then for all epsilon greater than 0, if the variance of f is small compared to pi star and epsilon, then inequality 1 holds for s equals 1 minus lambda of f squared. It means that if f is shrinking well, then s is very close to 1. In addition, if the variance of f is very small, then inequality 1 holds for s equals 1, which is better than any expanded Chernoff bound that we know of. We also prove a similar bound where the variance of f is larger, but then it's generally worse, and it depends on the variance of f, on pi star, and on epsilon. An interesting question is whether there is a similar bound where s equals 1 minus lambda of f, even when the variance of f is large. A few words about our proof of this theorem. So the proof is a generalization of a similar proof by Ankit Garg, Yin-Tat Lee, Zhao Song, and Nikhil Srivastava, where we show that the sampled average of f equals to a small martingale plus a small error, and then we use Azuma's inequality, which is like a Chernoff bound for martingales. So a quick comparison between the GLSS bound and R bound. R bound depends on lambda of f and not lambda of g. R bound applies to any stationary distribution and not just the uniform one. And also we have a special case for when the variance of f is very small, then s equals 1. Okay, so now we'd like to apply our expanded Chernoff bound for shrinking functions to mk plus. But first, let's discuss the eigenvalues of mk plus. According to a theorem by Kaufman and Oppenheim, given a gamma local spectral expander, if gamma is small enough, then the eigenvalues of mk plus are 1, and the other eigenvalues are in small neighborhoods around k plus 1 minus j over k plus 2. A few words about gamma being small enough. So according to a proposition by Dinur and Kaufman, for every gamma and d, there is an explicit infinite family of bounded degree d-dimensional complexes that are gamma local spectral expanders. It means that there are complexes with small enough gamma. So from now on, let's assume that gamma is small enough. Okay, so one more definition that we're going to use is the neighborhoods of mk plus. We denote them by wkj. So wkj equals to the span of the eigenvectors of mk plus with eigenvalues in the neighborhood of k plus 1 minus j over k plus 2. The word neighborhoods is a bit abused here, but still we call wkj the neighborhoods of mk plus. Now, as you can see, ckx equals to a direct sum between the span of 1 is the constant function 1, and wkj, where j goes from 0 to k. This is the spectral orthogonal decomposition of ckx by Kaufman and Oppenheim. Now we can apply our expanded Chernoff bound for shrinking functions to mk plus to get a high-dimensional expanded Chernoff bound for functions that come from good neighborhoods. So here we have the requirement that if f is from neighborhoods w, k, j plus 1 and higher, then if the variance of f is small, S equals 1 minus k minus j over k plus 2 plus a small value depending on gamma squared. For example, if f is in WKK, then S equals 1 minus 1 over k plus 2 plus a small value depending on gamma squared. So it means that if when k approaches infinity, then S is very close to 1 as long as the complex is a good expander, which is what we wanted. However, we still have one problem, and it's this requirement of f being in WKJ plus 1 and higher. Because when thinking about a high-dimensional expander Chernoff bound, we would expect a requirement about the complex itself and its links, some combinatorial requirement, not a spectral requirement about the eigenspaces of some walk mk plus. So our goal now is to turn this requirement of f being in the neighborhoods of wk j plus 1 and higher to a combinatorial requirement about the structure of the complex. For intuition, let's see what happens when k equals 0. So then we only have one neighborhood, W00, 0, and this requirement becomes that f has to be in W00, 0. And we can easily make this requirement a combinatorial one, because f is in W00 if and only if f is orthogonal to the constant function 1, which is true if and only if the expected value of f is 0. This is a much simpler requirement about f. Now, our goal is to generalize this requirement to larger values of k. This is why we define the level of a k-Cochain. So given a function f on k faces, it is from level j plus 1 if its expectation on the links of j faces is 0. For example, if k equals 0, f is a function on the vertices, then it is from level 0 if its expectation on the links of -1 faces is 0. The only -1 face is the empty set, and its link is the entire complex. So this requirement becomes that the expectation of f has to be 0. This example shows that our definition of the level of f being from level j plus 1, is a generalization from the requirement we saw earlier of the expectation of f being 0. A key proposition that we prove is that f is from level j plus 1 if and only if it is from neighborhoods wk, j plus 1 and higher. This proposition lets us go from a spectral requirement to a combinatorial one about the expander structure and its links. We use it to prove our main theorem, which is the high-dimensional expander Chernoff bound. So here, it's as before, except now we have the requirement of f being from level j plus 1. We also have a few extensions of this theorem. The first one is for cases where the variance of f is large, and we have already discussed this extension. And the second one is for cases where f is not entirely from level j plus 1, but most of its mass is. Note that we still have the requirement of gamma being small enough, and an interesting question is whether this requirement on gamma can be relaxed. Okay, so now we are basically done because this is our main theorem, but we also have our bonus theorem about the decompositions of ckx. First, let's define the up and the down operators. So the up operator, denoted djk, takes j-Cochains and returns k-Cochains, where k is greater than j. And the down operator, defined to be the adjoint of the up operator, takes k-Cochains and returns j-Cochains. A proposition by Kaufman and Oppenheim says that k plus 2 mk plus equals to one step up and then one step down, which really makes sense. Now, three decompositions of CKX that we're going to discuss are all, they all look like this. So they say that CKX equal to a direct sum between the span of 1 and VKJ, where J goes from 0 to K. In the first decomposition we have VKJ. In the second one, we have UKJ. And in the third one, we have WKJ. So the first decomposition is by Dickstein, Dinur, Filmus, and Harsha. It's called the DDFH decomposition. And here we have VKJ, which is the subspace of k-Cochains that come from j-Cochains that are in the kernel of the down operator. So if we take those j-Cochains one step down, they become 0. And according to DDFH, this is an almost orthogonal decomposition of CKX. Another decomposition by Kaufman and Oppenheim. Here we have UKJ, which is the subspace of k-Cochains that come from j-Cochains and are orthogonal to any k-Cochain that comes from j-1 cochains. This is the combinatorial orthogonal decomposition by KO. And the third decomposition we have already discussed. Here we have WKJ, which is related to the eigenspaces of MK+. And this is the spectral orthogonal decomposition by KO. We proved that when gamma is small enough, all of those decompositions are actually the same. And as a corollary, we proved that the DDFH decomposition is orthogonal. That's it. Now, to sum up, we proved the expander Chernoff bound for shrinking functions. We then proved a high-dimensional expander Chernoff bound for functions from high levels. And finally, we proved that when gamma is small enough, the DDFH decomposition equals both KO decompositions. Thank you.